Good evening. Welcome to the QCIS channel. We're all on this channel. You get a daily dose of science, technology, engineering, and math. And this evening, I'm going to give you a brief overview of what photogrammetry and land surveying is. Now, for the most part, photogrammetry, remote sensing, GPS, GIS, GNSS, they're all in the neighborhood of data spatial systems. You're collecting data and you're generally going to use it for plotting points and making maps. So without further ado, I'm going to go ahead and share my screen and I'm going to give you the definition of what photogrammetry is in land surveying. And when it comes to surveying, photogrammetry is the science of making measurements from photographs, especially to determine the exact positions of surface points. It's essentially using photography to create maps and models, and it can be done using aerial and ground-based cameras. Also, photogrammetry involves the process of extracting spatial information from photographs because it relies on the principles of geometry and trigonometry to measure distances, angles, and elevations based on the positions of objects within overlapping images. Now, what I'm going to do, I'm going to give you more of an overview from my PowerPoint presentation on photogrammetry. And in photogrammetry, again, here's a definition as well. It talks about the art and technology of obtaining information about physical objects and the environment by photographic and electronic images. Basic information. Mapping from aerial photos is the best mapping procedure yet developed for most large projects. Usually successfully, it's for maps or used successfully for maps varying in scale from 1 to 1 million down to 1 to 120 with contour intervals as small as 1 foot. Now, topographical mapping is the most common form. USGS, which is the United States Geological Survey, which is a government organization, updated and it's done this way. And it's used to construct a scaled three-dimensional optical model of the land surface by using a stereo plotter. Also uses aerial photos, the aid of aerial photos, geological investigations, soil surveys, land surveys, tax mapping, reconnaissance, and military intelligence, urban and regional development, transportation system investigations, quantity estimates, shore erosion, and can also use mathematical methods, and they've been developed to make precise three-dimensional measurements from photos, known as photo triangulation, three-dimensional positioning of survey stations. Photo has been used to take geometric measurements of human bodies, artificial human hearts, large radio telescopes, ships, dams, buildings, and very accurate reproductions. So basically, in general, photogrammetry is not economical for small projects. The cost break-even point is somewhere between 30 and 100 acres, and that depends on the situation. Now, besides some uses of photogrammetry, what are some non-uses of photogrammetry as well? Now, we deal with types of terrain. So photogrammetry cannot be used successfully over the following types of terrain: deserts or plains, sandy beaches, snow, also the photograph as uniform shades, because the photograph as uniform shades, it has little texture. Of course, deep canyons, high buildings that conceal ground surface, in areas covered by dense forest. And you have metrical photogrammetry, obtaining measurements from photos from which ground positions, elevations, distances, areas, and volumes can be computed and topographic or planimetric maps can be made. We also have photo interpretation, which is the evaluation of existing features in a qualitative manner. Types of photogrammetry, we have aerial, which is a series of photographs of an area of terrain in sequence using a precision camera. Terrestrial, photos taken from a fixed and usually known position on or near the ground with the camera axis horizontal or nearly so. And close range, camera close to object being observed, most often used when direct measurement is impractical. The history. Well, the first use of photogrammetry was by Arago, a French geodesist, in 1840. This included topographic and terrestrial. The first aerial photogrammetry was by the French in 1849, and he used kites and balloons. Laussedat was also French. He's the father of photogrammetry. Now, first an American, or the USA, but the first American, let's say the first American that utilized photogrammetry was DeVille, Surveyor General of Canada. And when I say America, not the United, I shouldn't say the United States, I should say North America, because North America consists of Mexico, Greenland, Canada, and the United States. So we're going to say the first North American was DeVille. He was the Surveyor General of Canada. And then USGS adopted photogrammetry as mapping in 1894. The mapping was a process, and the mapping was between Canada and Alaska. So that basically shows you that photogrammetry is nothing new. In fact, it's right around 185 years old. So some of us would think it's new. Now, it might be new in American surveying because Americans, they use tools like theodolites. They use plumb bobs, tapes, chains. But now when we deal with air, we can have a wider area that we can survey. Some more history. Airplanes brought great change to photogrammetry. First used in 1913, used extensively in World War I, photo interpretation, used in World War II, mapping for recon and intelligence, World War II to 1960, and used often, expensive and accuracy problems for engineering design. And after the mid-60s, advent of computer and plotting has made photogrammetric mapping accurate and, of course, affordable. Now, photogrammetry for engineering. Defined, photogrammetry is the process of measuring images on a photograph. Modern photogrammetry also uses radar imagery or radar imaging, radiant electromagnetic energy detection, and X-ray imaging. Now, this is called remote sensing, which is also in the area of spatial data and GIS. Surveying uses remote sensing. Categories of photogrammetric interpretation. Metrical photogrammetry, obtaining measurements from photos from which ground positions, elevations, distances, areas, and volumes can be computed, and topographic and planimetric maps can be made. We have photo interpretation, evaluation of existing features in a qualitative manner, timber stands, water pollution, soils, geological formations, crops, and military interpretations. And we have geometry of photographs, or we have orthographic projection. Now, when you deal with orthographic drawings, now some people have done it. Well, what you have is You have a top view, a front view, and you have a side view. And what you do, you draw projection lines to get the orthographic view. It's at a 45-degree angle. Now, what that orthographic view is going to produce is a 3D-like image. And, well, if you look at the orthographic projection, well, each point projected normal to a reference plane. Well, this is exactly what you're doing when you deal with orthographic drawings. And you're going to have, if you do this on a piece of paper, plot all the points, you're going to get an orthographic drawing as well from orthographic projection. Then you have perspective projection. Each point projected to a central point due to points being at different elevations. They look three-dimensional. Then you have the center of photo, or you call it, or we call it the principal point. It's located at the intersection of lines joining the fiducial points. Remember, the principal point, center of photo, located at the intersection of lines joining the fiducial points. Now, we get into a little bit of the calculations. Now, to form the calculations, one must know H, or we call it uppercase H, is the height above the datum from which photos are taken. F is the focal length of the camera lens, either in inches or millimeters. Items on the photo, the decimal points, date, then you have your roll and photo number. All right, you have your scale of your vertical photo. S equals F over uppercase H prime, or F equals uppercase H hyphen lowercase h. F equals focal length 6 inches or 152.4 millimeters is common. H prime, what we say uppercase H prime, is the height of the plane above ground. H is the height or the elevation of ground. H is also the height of place above the datum, the altimeter reading, 2% error. Now, the datum scale equals the scale which would be effective over the entire photo if all the points were projected downward to datum. Again, the datum scale is the scale which would be effective over the entire photo if all of the points were projected downward to datum. That's S subscript D, which equals lowercase f over h. Then you have your average scale, and that's for photo planning. That's S subscript AV equals f over uppercase H hyphen lowercase h subscript AV. And also average elevation can be determined for USGS topo maps. Again, average elevation can be determined for USGS topo maps, etc. Then we have our relief displacement. Now, relief displacement exists because photos are at a perspective projection. Use this formula to determine the height of object. Here's the formula: H equals D times H prime over R. That's uppercase H. We're trying to find lowercase h, which is the height of the object. D is the radial distance to top of the object, radial distance to bottom of object. So when something is radial, that means we have something round. So we're going to have a radius or a diameter, but we're dealing with radial. So we're going to have a radius or radii. And R equals the radial distance to the top of object. So that object could be a sphere. Planning and executing photo project, basic overall process. Number one, photography. You have to obtain suitable photos. Number two, control. Obtain sufficient control through field surveys and or extension by photographic methods. Number three, map compilation. That's plotting of planimetric and or topographical features. Number four, map completion, which includes map editing and special field surveys. And then number five, the final map drafting. Now, when we deal with the elements of planning, we have to go into conversion of requirements to project specifications. Factors. What is the purpose of photogrammetry? Well, the majority of projects for engineering involves making topographical maps in a stereoscopic plotting unit. So we have a wide range, we have a wide angle photography, which is 152 millimeters focal length. Again, we have a wide angle photography, 152 millimeters focal length or 6 inches is common, is required for topographical mapping because it provides better vertical accuracy. Now, if the area is heavily wooded, we use F equals 210 millimeters. That's a standard angle to allow more visibility through trees. Generally, 60% overlap with 15 to 30% side lap. So basically, orientation of flight lines is dictated more by economy than geometric considerations. Also, photos for mosaics should be flown as high as possible. Why? Reduces relief displacement. Then you have ortho photos, similar to topo maps, however, should be taken normal to ground topo. 2, photo scale, somewhat dependent on the type of plotter. Essentially can be dependent on the type of plotter you need to see and dividing it by the resolving power of the photo equipment. Also affected by map accuracy and area configuration. Allowed scale variation, this is number 3. Allowed scale variation, which is variation caused by difference in ground elevation and flying height. Then you have a longer focal length and it reduces scale variation. Now, if flying remains constant and ground elevation increases, which ground elevation will increase the area covered by the photo, once that happens, well, the photo becomes less. So again, if flying height remains constant and ground elevation increases the area that's going to be covered by the photo, then the photo becomes less. Then overlapping becomes less. And then you're going to need a viewfinder to control the overlap in flight line spacing, and thus that will eliminate the possible gaps. Then with relief displacement, that affects mosaics most. So basically, large amounts of relief displacement will make it difficult to form continuous picture desired in mosaics. Relief displacement decreases the flight height because flight height increases. Again, let me make it plain and simple. When relief displacement decreases as flight height increases, the focal length must be increased. Also, relief displacement has no adverse effect on map making with stereo. So with greater relief displacement, elevations can be measured and plotted more accurately. And with tilt, the amount of direction of flight, which is known as Y tilt, will cause overlap to be greater on one end than other. Again, amount and direction of flight, Y tilt, will cause overlap to be greater on one end than on the other end. Then you have the X tilt, amount normal direction of flight, will increase side lap on one side and decrease on the other side. Y tilt is corrected by viewfinder. X tilt is corrected by increasing planned side lap. Crab and drift. So when we deal with crab, that is the angle formed between flight line and edges of photo and direction of flight and caused by not having focal plane square with direction of flight at time of exposure. So basically, it's corrected by the rotation of the camera on a vertical axis through a viewfinder, and it also reduces coverage, but side lap compensates. And then the drift, it's just the plane not staying on the flight line. Most common cause of reflights and gaps. Flying height determined after side lap and overlap determined. Here are the factors affecting it. Desired scale, relief displacement, and tilt. Then you have the precision of equipment used. So with greater precision, again, with greater precision, you're going to have the greater possible flying height. So by doubling the flying height, ground coverage increased 4 times, thus less ground control and fewer photos. So vertical accuracy, most important in topographical mapping. And this is where you need flying height because it's related to contour interval, and that is desired. Flying height is desired for contour interval. The relationship called the C factor or the precision factor. Flying height equals desired contour interval times C factor. C factor is the value used to compute flying height, which will produce photos satisfactory to obtain the desired vertical accuracy of maps. Then you have direction or orientation of terrain. So you have to arrange to fly along ridges, not across ridges. Gathering material and people. Utilize existing photos, maps, survey data, instruments, and personnel. You also have to determine specifications and conditions for operations. Then you prepare final plans, and that would include scheduling and surveying instructions. And then you have to look at the cost estimating and replanning. So flight design. A, considerations. 1, you need project boundaries. 2, existing and planned control. 3, you need a time schedule. 4, there's a final product needed. 5, optimum flying season. 6, bound cover conditions. B is your objectives. So you have to determine optimum conditions for spacing of photos along flight lines. Number and spacing of flight lines to cover area. Again, you need number and spacing of flight lines to cover area. 3, plan must account for allowable deviations. And then you must have the distance between the flight lines on flight way. Flight design. Well, you're designing a flight pattern. Flight patterns are totally dependent on overlap and side lap. So under ideal conditions with a 9-inch by 9-inch photo with 6-inch photo length and overlap of 57% and side lap of 13%, it will provide maximum stereo coverage with no laps. Now, if additional safety factor is desired, again, if additional safety factor is desired, overlap can be increased to 70 to 75%, and side lap can be increased to 50%. Computation of flight plan. They are required to compute flight map lines, time interval between exposures, and the amount of film needed. Number 1, focal length of camera. Number 2, flying height above datum or photo scale for certain elevations. Then you need the size of photo, size of area to be photographed. Then you need positions of outer flight lines with respect to boundary, overlap, side lap, scale of flight map, and then the ground speed of aircraft. And I'm going to give you an example. You have an area 15 miles north-south and 8.5 miles east-west. Photos 9-inch by 9-inch. Scale 1 to 12,000 at 700 feet above elevation. Overlap 60%, side lap 35%. Ground speed of plane 150 miles per hour. Flight lines to be laid out north-south on a map at a scale of 1 to 62,500. Outer flight lines coincide with the east and west boundary. Well, here you have the flying height. You have H equals 12,000 above 700 feet or 12,700 feet above sea level. Then you have the ground distance between flight lines, since side lap is 35%. Photo between lines is 65% of 9 inch, and you get actually 5.85 feet. And then you put that into the ground spacing formula. And what you're going to do, you're going to convert inches to feet. Actually, that's 9 inches equals 5.85 inches because that's 65%. So you have 5.85 inches, and you're going to multiply it by 12,000 feet. Then you're going to divide by 12 inches, which equals a foot, and then you get 5,850 feet. So you're going from inches to feet. Then you're going to find the number of flight lines. So you're going to find the total width, 8.5 miles, and you're going to convert miles to feet. And what you're going to do, you're going to use the number 5,280. Well, 5,280 feet equals 1 mile. So when you multiply 8.5 miles times 5,280 feet, you get 44,880 feet. So then you take that number, 44,880, and then you divide it by your ground spacing answer, and then you'll get your flight lines. So you get 8 plus 1, which equals 9. Now, you're going to always round up. So if you have 8.4 or 8.1 or 8.2, you're going to round it up to 9. It's going to be the whole number. And then you have to adjust ground distance between flight lines. So again, you're going to take 44,880, which is your total width, and you're going to divide it by your flight lines. And what you're doing, you're going to get your ground distance. And then you're going to take 5610 and divide it by 62,500, which that's your scale. And that's what your spacing is going to be on your map. So at 5,610 feet on a map, in which you have a scale of 1 to 62,500, your spacing is going to be 1.08 inches. So again, you're going to take your feet and you're going to convert your feet into inches. And finally, ground distance between exposures with 60% overlap gain on each photo is 40%. So 40% of 9 inches is 3.60. And then ground distance is 3.60 times 12,000. Also going to convert every number from inches to feet, and then you're going to get 3,600 feet. And once again, when we deal with photogrammetry, photogrammetry and land surveying is the science of making measurements from photographs, especially to determine the exact positions of surface points. Again, in surveying, photogrammetry is the science of making measurements from photographs, especially to determine the exact positions of surface points. It is essentially using photography to create maps and models, and it can be done using aerial or ground-based cameras. And to take it a little further, photogrammetry involves the process of extracting spatial information from photographs as well, because it relies on the principles of geometry, trigonometry to measure distances, angles, and elevations based on the positions of objects with overlapping images. And that concludes this series, or that concludes this topic on photogrammetry for land surveying. If you like what I just presented, please comment, share, and subscribe. And if you're looking for some social and political content, check out my main channel, the 401 Talk Zone radio show channel. Now here's where you can find me. For the 401 Talk Zone radio show, you can find me on YouTube, X, formerly Twitter, Rumble, and Truth Social. And here on the QCIS channel, you can always find me right here on YouTube, X, formerly Twitter, and LinkedIn. And before I go, I want to wish you all a happy Easter. This is the day Christ rose again. And remember, if you believe in Christ, Christ gave up his life for us. And once again, I thank you for viewing this content of photogrammetry and land surveying. Photogrammetry and land surveying from the QCIS channel. So on this channel, you get a daily dose of science, technology, engineering, and math. Until next time, my name is Leon Jones. You all have a wonderful and gracious evening. Happy Easter. And remember, these videos, you can see new videos between Thursday and Sunday, right here on the QCIS channel, your home for STEM. And again, once again, thank you for visiting this channel. Again, my name is Leon Jones. Please have a wonderful and safe Easter.